Hello, we are the Galaxy Classification Team for the NASA SEAS 2024 internship program, and our project is on Gaia Vari mapping the Milky Way.
Hi, my name is David Yang, and I'm from Fairfax, Virginia.
My name is Rishi Tripathi, and I'm from Mansfield, Massachusetts.
Hi, my name is Natalie Bell, and I'm from Temple, Texas.
We had three goals for this project. Our team wanted to look at the frequency and distribution of the different variables in our Milky Way. We did this by using the data we acquired from Gaia. Next, we used the parallax measured for each of the subjects to calculate the distances to the variables. We did this to determine the absolute magnitudes of the variables. Lastly, we determined a period luminosity relationship for a specific type of pulsating variable, which we then compared to the previously observed relationships found in previous studies done by researchers. Types of variables. Cepheids, aurora Lyrae, long period, and delta Scuti are all different types of pulsating stars. This means that they expand and contract periodically. So the picture on the right is an example of a pulsating star. The eclipsing and ellipsoidal binary systems are not just one star, but a system of stars. The picture on the bottom right is a binary system. So this will also be expanded upon later in our presentation. Physical properties. The way we classify all the data received by Gaia is by looking at the properties of the variables and comparing them to perfect examples. Apparent magnitude is how bright an object looks as viewed from the Gaia spacecraft. Absolute magnitude is how bright an object looks when viewed from 10 parsecs away. 10 parsecs is around 32.6 light years away, which is around 192 trillion miles away. So it's very far. And the period is the time it takes for the star to complete one full cycle of its brightness variation. So the contraction and expansion makes the star dimmer and brighter, respectively. Parallax. Parallax is the observed displacement of an object caused by the change of the observer's point of view. This change in point of view is caused by the Earth's movement around the sun. It's a great method of measuring distances to these variables, which greatly helps us map the Milky Way. This will also be expanded upon later in our presentation.
Okay, to begin, I will be describing the process that we used when classifying the different types of variables. First, we worked to classify Cepheid type pulsators, which are pulsating variable stars. On the slide is an image of one of the Cepheids that we classified. This image shows that this specific Cepheid has a period of 1 day and 20 hours, which aligns with the average of 1 to 200 days for Cepheids. This image also includes a diagram that helps us determine the color value of a specific subject, which is typically 0.2 to 2.3 for Cepheids. You also notice that there is a distance modulus on this image. This will be explained further by David later on in this presentation. On this slide, we also included an HR diagram or Hertzsprung-Russell diagram that we use to determine the absolute magnitude of Cepheids, which is usually -6 to 0. On the slide, lastly, we included an image that shows multiple examples provided by Gaia that we utilized while classifying variables. Okay, next we work to classify our Lyrae type pulsators, which are also pulsating variable stars. Our Lyrae type pulsators typically have a variability period of 0.2 to 1 days, an absolute magnitude range of -1 to 1.5, and a color value of 0.3 to 1. Okay. We then work to classify delta Scuti type pulsators, which are pulsating variable stars with variability period of 0.02 to 0.3 days or 0.5 to 7 hours. We also classified long period variables, which are also pulsating variable stars, but with long variability periods of 10 to 1,000 days. Okay. Lastly, we classified eclipsing binary systems, which consist of two closely orbiting stars that have an absolute magnitude range of 2 to 7, and ellipsoidal binary systems, which consist of two close stars moving in an elliptical orbit with an absolute magnitude ranges that are typically -1 to 10. This next slide includes a pie chart that shows the distribution of the 374 different variables that we classified. Of these variables, Cepheids are the least common, but the most important. They're the best standard candles and are used for distance determination for very distant objects, for which the parallax is not measurable. They have a period luminosity relationship in which the variability period is closely related to their luminosity. And delta Scuti type pulsators are our Lyrae type pulsators, and long period variables can also be used for distance determination if Cepheids are not present.
So now that we've classified our Cephids, what we can do with them is we can calculate their absolute magnitudes. And why their absolute magnitudes are important is because, as Natalie mentioned earlier, Cephids tend to follow a period luminosity relationship, or there is a positive correlation between the length of their pulsation period and their absolute magnitude, which is just a measure of their intrinsic brightness. And so in order to find their absolute magnitude, first we need to find their distance. And this we do through the parallax method, as mentioned earlier. As you can recall, the distance in parsecs is equal to the reciprocal of the parallax angle in arcseconds. And after getting the distance, we can also find the apparent magnitude. And this is basically just the average brightness that the Gaia telescope records when viewing the star. And so once we have the distance and the apparent magnitude, we can plug this into the distance modulus equation from earlier and use this to solve for the absolute magnitude. And this is what we did for each of our Cephid variables that we classified. And so looking here, we were able to plot it on our own Cephid period luminosity relationship. You can see that there's a positive trend in terms of the log of the period and the absolute magnitude. Our graph is the one on the left. You can see it follows a similar upward trend as the graph on the right, which is a study taken by the Hubble Space Telescope, and it was observing several nearby Cephids. Also for our graph, you may notice that we have 20 Cephids plotted, which is more than the 7 we classified. And the reason for that is we added 13 previously classified Cephids to our data set in order to improve the accuracy. And as for the accuracy of our own Cephid period luminosity relationship, we looked at a different study by Lazovic et al., which also established a period luminosity relationship. And the slope of their trend line was negative 2.67 plus minus 0.17. And our own empirical slope for our trend line was negative 2.65 plus minus 0.477. So very close with a percent error of only 0.75%. However, where our trend lines deviated was in the y-intercept. The established one was negative 1.58, and our empirical y-intercept was negative 0.495. And so there are a couple different reasons for this error. One is that we used a smaller sample size. We only used 20. And so there's a chance that this sample wasn't a good representation of all the Cephids out there. In addition, we didn't have any spectroscopy data from Gaia. And why this is important is there's actually two different types of Cephid variables. There's type 1 and there's type 2. And they are made out of slightly different elements that would be able to be distinguished on if we had spectroscopy data. And these type 1 and type 2 period Cephids type 1 and type 2 CFIDs display slightly different period luminosity relationships. And so there is a chance that our graph is slightly skewed, as edge cases from type 1 and type 2 could have served to slightly skew the data. Finally, another reason for the error is that studies have shown that there can be a slight inconsistency with the CFID period luminosity relationship depending on where they are in the galaxy. So the CFIDs in our galaxy may demonstrate a slightly different relationship from CFIDs in another galaxy. However, this discrepancy isn't big enough to discount their usage in calculating distances, so we still use CFIDs. Now moving on to our RR Lyrae variables. We also attempted to do the same thing at establishing a period luminosity relationship between the log of their period and their absolute magnitude. However, as you can see here, there really wasn't a great correlation between period and absolute magnitude like we had with the CFIDs, at least in the visible light wavelength, which is what we were observing. So rather than try and establish a positive correlation, what we did instead was calculate a range of distance errors given an apparent magnitude. And so as you can see here, given different apparent magnitudes or apparent brightnesses from Earth, we can calculate a range, a distance range in which this R Lyrae variable might be located. And as you can see here, as the apparent magnitude increases, which just means that the star gets dimmer as it appears to us, the range and distance increases. So this means that there is a greater error margin in which our distance calculation is in. And you can see this in the graph as well. The higher the apparent magnitude, the larger the distance between the possible minimum and maximum distance. And we calculated these errors using the standard deviations of the absolute magnitudes, and we used that to calculate our error for the distances. Moving on to applications of our research. So one of the main goals of Gaia is to understand our own galaxy better and ultimately create a three-dimensional model of our Milky Way that can be used for many different purposes. And so our research helps with that by being able to calculate accurate distances within our own galaxy so that we're able to map the location and distances of different stars or systems. In addition, our research helps to establish a cosmic scale and measure distances outside of our galaxy as well. So this is with the CFID period luminosity relationship. Even though there were some errors with our own findings, it was close enough that using such a relationship would be able to produce a reasonably accurate estimate for distances outside of our own galaxy. At the very least, a lot more accurate than parallax methods at that distance. And finally, it helps us understand the distribution of the different variable systems and stars in our Milky Way galaxy. So this is what we did earlier with the statistics. We're able to find the general trend of which stars and which systems are rarer than the others. And if you can see here on the right, the photo on the top was a CFID variable discovered by Edwin Hubble in 1923, and it was later revisited by the Hubble telescope in 2010. And you can see it's a CFID in how the brightness pulsates over time. You can see it starts off dimmer and it gets brighter over time. And this is actually a CFID found in the Andromeda galaxy, which is further away than our own galaxy. And so you can see that CFIDs are able to calculate, we are able to use CFIDs to calculate distances in galaxies further away. And as for our experience at SEAS, personally, I really enjoyed it. Just being able to do real research in a professional work environment, I think was really great. And we learned a lot from our mentors and just being able to make connections with professionals, as well as we had a lot of speakers come in and give us advice about college and our future. And I think it was a really great experience, and I'd highly recommend it to anyone who's interested.
I love the balance we had between fun activities and work. During our 2-week internship, we went to Six Flags, Dave and Buster's, the NASA Johnson Space Center in Houston, and other fun activities, along with long and exhausting working days.
I also really enjoyed this internship, and I'm very grateful that I was able to conduct research within a field that I aspire to pursue in the future. So here is just a list of the references that we used while completing our research project. And just to conclude our presentation, I would just like to thank you for your time and for listening to us present our presentation.